All right, so is everybody already aware of the Career Expo today over at the Rec Center? I see some people are a little bit more dressed up than usual. Probably some of that's related to the senior design presentations this afternoon, but then hopefully it's also a good coincidence that we've got the Career Expo. There's a lot of opportunity over there. You know, you can do just about anything you want with a civil engineering degree. You just have to go find the place to do it. So a lot of people have driven from hundreds of miles away to try and recruit students. They're really eager to talk to people, and even if you think you've got the perfect opportunity already lined up, it doesn't hurt to just see what else is out there, get a feel for what's available. So I'd encourage you to go over there. It's until 4 o'clock in the Rec Center. Homework 8 is due on Friday, and I've got a couple of hints, and of course the examples that we're going to work through today also will inform how you can solve that assignment. And then looking a little bit to the future, in next week we've got homework 9 due on Wednesday, then the design project phase 2 due on Friday. So you're going to have a very full 2 weeks, and then things kind of cool off and slow down during spring break. So any schedule or announcement questions before we pick up where we left off on Monday? If not, this is where that was. We were working on a specific energy diagram. Remember, a specific energy diagram is where we look at all of the different depth possibilities that yields the same flow rate being carried through the same channel. So we've got maybe a channel that's 4 meters wide. The water depth is determined by the slope of the channel, and there's this same flow rate going through it, but there's an infinite number of possible depths associated with whether we have a really shallow slope, a really steep slope, or something in between. So what we had prepared in class on Monday was this specific energy diagram, where this was the channel width, this was the flow rate for the example, and then at a variety of different depths, we found what would be the corresponding cross-sectional area, the resulting velocity, and finally the specific energy, which we define as the depth plus the velocity head. And the velocity head can be calculated by v squared divided by 2g, or the velocity head could be q squared divided by 2g a squared. So specific energy is just measuring how much energy is there in the fluid above the bottom of the channel. And this is the diagram that we put together in that example. And the critical point that we identified, the farthest to the left point on this figure, is associated with the critical depth. That also is the depth that would give you a Froude number of exactly 1. Remember flow regime and how we can calculate the Froude number? So a Froude number of 1 is what you'll get if you put in the critical depth to the formula for the Froude equation. Here we saw, here's the Froude number squared is this. So to get the Froude number itself, you do the square root of q squared times b divided by g a squared. So if our depth in this example, the critical depth was 0.86 meters, if you calculated the Froude number, that would be exactly 1. So in any depth that's less than the critical depth, then the flow is supercritical because the velocity is high. So here in this range, we had high velocities. The energy is high because of the big velocity and its supercritical flow. Any depth that's greater than the critical depth, this region above the dashed line, is subcritical flow. So the second part of the example that we wanted to look at was the alternate depth. So this phrase alternate depth is used in your homework assignment on Friday. You're asked to calculate the alternate depth. So we'll do that here. There is a depth. How much specific energy is there when the depth is 0.5 meters? Let's see if we've already got that here. So we don't. We've got where the depth is 0.2, 0.4, 0.6. Let me just add another row into this example, and we'll calculate when the depth is 0.5, what is the, what's the specific energy. So let me put in the 0.5 for the depth. I'll just carry through the same formula for area, velocity, and specific energy. So let me look at one more digit of precision here. So what we're going to say is the specific energy when the y equals 0.5 is 1.774 meters. And that's the units of specific energy. It's energy measured in units of length. Okay, so let's look on the figure here. Here's our 0.5. So follow the curve over, and look, here it's intersecting the specific energy diagram at 1.774. So there's another depth that has the same amount of specific energy. So let me just draw a line on here to make it completely explicit what I'm talking about. I'm talking about, here's the crossover point for where, let me move the critical depth label out of the way. And then just to distinguish this from other things. All right, so this is where the depth was 0.5. It's got a specific energy of 1.77. The alternate depth with the same amount of specific energy, it looks like it's about 1.6 meters. So let's look over here in the data. So here is 1.774. This is pretty close to 1.774. It's 1.72. Let's find out exactly what is the depth that would make this equal to 1.774. So is it 1.61? That's getting closer. 1.62. It's getting closer. Of course, rather than doing it manually, we can do a goal seek if we know what is the target value we're looking for. We want this to be 1.774 by changing the depth, and then that's going to tell us what is the alternate depth that has the same amount of specific energy as here. So here where the depth is 0.5, the specific energy is 1.774, but there's another depth that has the same amount of specific energy. And so y equals 0.5 meters and y equals 1.66 are alternate depths. So what is an alternate depth? Who can just paraphrase? What does it mean that two depths are alternates? Harley, I think you've got it. I can see it. They're both acceptable in what sense? What do they have that's the same? Yes?
Where they both have the same specific energy.
They have the same specific energy. So in parentheses, I'll write here, they have the same specific energy. Good. Okay. So we don't have to solve this with the spreadsheet. We could solve this question with this equation. So when the depth is 0.5, how much energy is there when the depth is 0.5? Well, we'll put in this for y, and then q squared divided by 2ga squared. So Q is 10 cubic meters per second squared divided by 2 times G, 9.81 meters per second squared, and then A squared. The depth is 0.5 meters by 4 meters because this channel is 4 meters wide in this example. So the area, if it's half a meter depth and 4 meters wide, then the area is 2 meters. So y plus q squared divided by 2ga squared. And so this is 1.274 meters. And then obviously this is 0.50 meters. So if we add it together, the E is 1.774 meters. Okay, so if the energy is 1.774 meters when y equals 0.5, what other depth has that same amount of energy? Is there another depth that gives us that same amount of energy? So we could solve this with an equation by saying E equals y plus q squared divided by 2g a squared. And that's y plus q squared divided by 2g 4y squared. Because here the channel's 4 meters wide and y is the depth. Okay? So let's substitute in some values. 1.774 meters is equal to y plus 100 divided by 2 times 9.81 and then 16y squared. I just substituted in the q of 10, which was in the numerator there, and squared it. All right, so if I take this a little step further, it's 1.774 is equal to y plus 0.3186 divided by y squared. Okay, and then I'll multiply each of these terms by y. So now I've got y squared, 774 y squared is equal to y cubed plus 0.3186. And what we've got is a cubic equation. So y cubed minus 1.774 y squared plus 0.3186 is equal to 0. So let me bring this up on the screen, just so those who are going to watch this later on have it. What we did is substituted in the original given depth of 0.5, found out how much specific energy there is, and then we say, what's the other depth with the same amount of specific energy? So set that equal to the E, the known specific energy, and then we arrange this cubic equation. Now your calculator, you've got the Casios, right? Most people in here have the Casio. I don't. I use a different calculator, but you can solve for what are the 3 roots of a cubic equation. And if you do, you'll get a negative root, which to us has no meaning whatsoever. We can just immediately throw that one out, the negative root. We'll get the depth that we already knew, 0.5, and then finally we can get 1.658 meters. And lo and behold, that happens to be the same depth that we found when we were doing it with Excel. So it'll tell you what are the depths of y that would give you the correct amount of specific energy. And so 0.5 and 1.658 are alternate depths. One of them is the supercritical flow depth. The other is the subcritical flow depth. So in this example, remember that the critical depth was 0.86 meters. So if you have water flowing along at a depth of 0.5, then that corresponds to supercritical flow conditions, because the depth is low, the velocity is high. This is the subcritical root. And it's important to be able to not only solve this cubic equation, but then also know which root to pick. So we're going to have, in non-uniform flow, when we analyze the water's reaction to some sort of a disturbance, we'll solve cubic equations a lot. You're going to probably solve 20 or 30 of them this semester. So this is number 1 out of 30. Then once you solve the cubic equation, you have to pick the right root. And oftentimes you'll know which root to pick because you will have analyzed weather conditions prior to the disturbance upstream. Was it supercritical or subcritical? And then that'll guide you most of the time on which route to select. So does anybody have questions about this before we move on to WaterGEMS? Actually, I have a homework hint for you before we move on to WaterGEMS. Let me give you that hint now. All right, problem 1125. There is a channel that looks like this, and they want to know what is the shape of the channel that would give you the lowest cost for construction, where they're saying construction has two main components. One is the cost of the lining, so that is, like if you were going to put down some sort of a plastic or concrete, some sort of a lining to prevent water from being infiltrated into the soil. So there's the cost of the lining and the cost of the excavation. So you want to minimize the total cost that can accommodate the flow. How big should this channel be? And then what's the slope required to carry a certain amount of flow? So let me step you through the thought process that you should have in this problem. Here's the geometry. There's a certain unknown depth. There's a certain bottom width that's not known. They do tell you the roughness of the material, that it's lining, so 0.014 is the end value, and then they define the side slopes as 1 to 2. So you can see what that means, and then the implication of it is that the width of that side section is 2 times the depth of the water. All right, so for that shape, they want you to find out what does it have to look like in order to have a flow rate of 10 cubic meters per second and a flow velocity of 0.715 meters per second. So calculating the area that's required is pretty straightforward. Remember, A equals Q divided by V, so that's easy enough. So find the area, and then there's a lot of different possible combinations of depth and bottom width that will give you that area. There's an infinite number of combinations, but there's only one combination of bottom width and depth that's going to minimize the cost. So you should prepare some equation that calculates the wetted perimeter based on what is the depth and what is the bottom width, B, because wetted perimeter is one of the costs. The lining, the cost of the liner is based on the wetted perimeter. The cost of the excavation is based on the area. And then I suggest that you incorporate a spreadsheet for solving this one, and you set it up so that you have a lot of different depths, and then for a certain depth, what would the B need to be in order to get the required area? So for example, if your depth is 0.2, there's going to be some certain bottom width required in order to achieve the required area that gives you the velocity and the flow rate that's needed. Okay, and then for every possible depth and width, what's the volume of soil that's being excavated? So how many cubic meters of soil are being excavated for every length, for every meter of canal that's built? So, like if you built 100 meters of it, then, how many cubic meters of soil are being excavated for every meter of length is how you can calculate the volume. And then once you know the volume that's excavated for that depth, what's the cost of excavation? And the problem gives you the parameters on how much it costs per cubic meter. And so this would be dollars per meter of length. And then same thing with the wetted perimeter. They tell you what's the cost of lining, so you can calculate the lining cost for that depth and the total cost. And so play around with all the possible combinations of depths and bottom widths, and then find out which is the one that gives you the lowest cost. And so you can do that manually. You could use Solver. Here on the Data tab, if you've got Solver added in, then you can do minimize by changing the constraint of the depth. But that's my recommendation on how you approach that problem. I think that with these hints, you'll be able to kind of get a feel for what the problem is asking you to do and calculate the lowest cost. And then once you know the lowest cost and what the shape is going to be, so you've defined how deep the water will be, what is the width of the channel. Then you'll put it into Manning's equation, and the only unknown will be the slope. Because you'll know Q, you'll know the shape of it, you'll know the lining roughness, and so S will be the only unknown for part B. Yeah.
Just one question. If you're doing like a real design,
Uh-huh.
would you go all the way to the top of the channel, or would you go like 2/3 of the way up?
Yeah, so you'd want to provide what's called freeboard, right? Yeah, so you'd want some extra capacity. So we're neglecting the necessity of freeboard here. Yeah, and later on the semester when we do channel design, we'll talk about how much freeboard do you want to provide for things like wind-driven waves. If you're going around a curve, there's super elevation of the water, safety factor for additional capacity. But here, just make it tall enough and assume that the water's just about to spill out of the top.
I guess the reason I ask is because I think I remember from fluid mechanics where we said 2/3 of the channel.
Yeah, it's a good rule of thumb.
Okay.
But here, make it 100% deep. Yeah. Okay, so now we're going to spend the rest of our class time, about 25 minutes, revisiting WaterGEMS. And now that you have estimated your demand for the hypothetical town that you're working on, your next step is to figure out how big should the pipes be. And what it says in the handout I've given you is that the pipes should, at a minimum, have 240 kilopascals, and at a maximum should have 850 kilopascals. So the pipes are going to always be the same pipe. Like once you put it in the ground, you can't change the pipe diameter to be big in the day and small at night. You know, you're just going to put in one pipe size. And so what impacts the pressure change throughout time is that during the day when there's a lot of demand, there are going to be a lot of head losses through the pipes. And so the pressure at certain junctions is going to be low during the day, during the peak flow capacity. And then at night, when there's hardly any water flowing through the system, when there's effectively zero frictional losses, then it's just going to be the static pressure that determines the pressure in the system. So how high on the hill you put the reservoir determines the maximum pressure, and the minimum pressure is determined by the length of the pipe, the diameter of the pipe, and then the elevation of the junctions. So we're going to play around with all those details today in another example. You could just, the simplest design is to make every pipe really, really big, but that's expensive and unnecessary because it's possible to meet these criteria with pipes that are much smaller than the maximum available that's available for commercial purchase. So for simplicity in today's example and also in the project, assume that all of the pipes are buried at some offset of the ground elevation. So you're given a map, a contour map. I've provided that big 11 by 17 map, and it has like elevation contours on it. You'll need to know what is the elevation of the ground at every junction. And then what you can assume is that either the pipes are at ground level, and then in the back of your mind you know that reality they'd be buried maybe 1 meter deeper, or you could actually put that into the WaterGEMS. You could have the pipe junction be 1 meter less than the ground elevation at that location. So, but just for simplicity, assume that you don't have a variety of pipe depths beneath the ground surface, that it's all the same amount of depth between the pipe and the ground surface. So in phase one, what you did is you said what would be the required flow rate at the peak design condition. So whether it is the peak day plus fire or the peak hour, for every one of those junctions, you know now what is the flow rate that has to be accommodated. So in phase two, what you're answering is the question, what size pipe is needed? And it's an optimization process where you're going to play around with a lot of different pipe sizes in a lot of different locations to find out what's the minimum pipe size that's acceptable. A secondary part of part two is figuring out where to put the reservoir, Because if you have the reservoir low on the hill, then your network isn't going to have much pressure. If you put it too high on the hill, there is such a thing as too much pressure, right? 850 kilopascals is the maximum pressure. And the reason for that is that oftentimes people's water heaters will begin to leak if the pressure in the network is too high. Or if someone turns the faucet and suddenly the water's coming out at an uncontrollable rate, there is such a thing as a maximum allowable pressure. So we're going to aim between 240 and 850, both in the example today and in the project. And if you over-design the pipe size, your pressure will be fine, but the cost is unnecessarily high. And if the pipe is too small, then the pressure is below the allowable limit, and that can cause either safety problems if it's the fire department trying to put out a fire using one of the hydrants, or it could be a health risk if the pressures are so low that there's backflow into your network and contaminants get into the water. So the minimum pressure is something that we have to keep right at 240 or above. Oops. So your prime directive here is just to make the pipes barely large enough to satisfy this criteria. Put the reservoir as high as possible on the hill without going over 850, because the more pressure you start with, then the smaller the pipe sizes can be and still get above the 240 kPa minimum. All right, so I handed out a paper copy of this. Were there any extras? All right, so open up WaterGEMS and let's create this network just with a new hydraulic model. And does anybody remember what are the preliminary things we do in WaterGEMS, just as a starting point? We've looked at WaterGEMS before, right? So we want to set the units to SI and make sure that it's calculating friction using Darcy-Weisbach. So first thing here, tools. No. Let's see, where is it? Yeah, tools, then more to get at the options. And then let's make sure the units, okay, I'm in SI because that's what it was in last time I ran the program. If this is your first time and it says US customary, change it to SI, click OK, close the program and open it again. It needs to kind of start from scratch already knowing that SI is the unit system. So that's the first preliminary thing we do is here under the Tools tab, More, Options, Units, SI. The other kind of preliminary thing is under the Home tab, go into the options here, and for the base calculation options, double-click that and make sure instead of Hayes and Williams, it says Darcy-Weisbach, because we want maximum accuracy on our friction calculations, and I don't care if it takes the computer a half second longer to do those calculations. So Darcy-Weisbach, and then close the window. All right, so now we're just going to draw a sketch that looks approximately like what this does, a schematic. It doesn't have to be to scale. So I'm going to start by this Layout tab, click on Layout, and you can see the first thing it's got is junctions. And so I'm going to click here. That's going to be A, and move some distance away. This will be B. This will be junction B. Here is junction E, F. I'll connect back to A, and then right-click to change from junction to reservoir. And so you see how the cursor now looks different. It was a circle before. Now it's a trapezoid representing a reservoir. And I'll just click that someplace and then finally escape. So your schematic should look something similar to this. Doesn't have to be in the same location. The lengths don't really mean anything since we're going to do user-defined lengths overriding it. Okay, let's start by renaming the junctions, and so the easiest way to do that is in the flex tables. So go here to flex tables and the junction. So instead of J1, let's call that just A. A, J2 is B, J3 is E, F. Okay, so those are the junctions. How come I don't have the option to rename R1? Well, R1 isn't a junction, it's a reservoir. So it has a flex table of its own. You'll see that the column next to that is the elevations. And our example does tell us what is the ground elevation for each one of those junctions. Let's put that in. Let's enter in the ground elevation. So for A, it is 0. B, 9.4. E, 2.1. And F has an elevation of 5.5. Okay, we've got the elevations defined. Now, if you look in the sketch, it tells us how much water is coming out at each junction. There's 350 coming out at B, 450 coming out at E, 50 coming out at F. So let me define all of that through demand collection. So the demand collection for pipe A is 350, and it's already in units of liters per second. Okay, I can close that. For wait, that wasn't, did I put that in A? There's no flow in at A. I need to change that, so I'll delete it. That's actually, okay, so I've deleted it at A. That should be at B. Sorry for that mistake. So 350 is at B. At E, put in a flow of 450. And at F, put in a flow of 50. Okay, I think I've defined everything that I want to for now. Let me annotate the junction. Since I'm working on junctions right now, let me right-click where it says junction. Well, let's expand the list. See where it says label right now? It's got the names of them. Let me also have it annotate. So right-click on the word junction, new, annotation. Let's have it do the pressure. So for a field name, drop down to pressure. And then I'm going to do a prefix of P equals. And just as a default, let's see where the offset of -2, -2 gets us, and apply. And that seems like it's okay. It's not right on top of the junction. That's an all right place for it as a default. Now there's no pressure calculated yet because I haven't run the model yet. Okay, so I've got the junction labels and pressures annotated. Let me put on some more annotations. So I'm going to annotate the junction elevation. And so I'll define that as ELEV equals. And the last one I did at -2, -2. So let me do that at -2, -5. Okay, so I've got the elevation annotated now. Okay. And let's also put on new annotations for flow. Let's annotate that as, I think, demand. So Q equals, we may have to come back and change that one. -2 and -7 for the offsets. Maybe -8. I like the spacing to be at least somewhat even. All right, so no flow rates yet. All right, let's take a look now. Since we've been through the junction and a flex table, let's go through the pipe flex table, because we need to update the lengths and diameters. So go into the pipe flex table, and What it's calling right now is P1. That's actually pipe AB. I'll just name all of these pipes by their starting and ending nodes. So BE, EF, AF. I won't bother renaming that other one. Maybe I'll call it RA for the reservoir to junction A. Okay, diameter. It thinks that all of them are 152.4 millimeters and ductile iron. So let me update that to what I know. I've got here on the map, it gives me the actual length, diameter, and then all of these are cast iron. So if I want to change all of them from ductile iron to cast iron, I think I can set them all at once. If you right click on the word material, global edit, then I'm going to do set. Maybe global edit works better when it's a numerical selection, because I don't see an easy way to choose the drop down. So let me choose from the material library cast iron. I guess I got to do that one by one. I wonder if I try the global edit and I just type in the word cast iron, I wonder if that'll work. It says it, but whether it knows it's cast, yeah, it looks like it is. Yeah, it said it, but I don't think it had the property. So don't do the global edit thing. We do have to select cast iron, because when we do select cast iron, what it's doing is it's telling it this roughness. See here where it says roughness height 0.0003? That is the K sub S value it's going to use when doing the Darcy-Weisbach equation. So we got to make sure that it knows the correct roughness height for each one of those pipes. So cast iron, does it know the roughness height for each of the pipes? All right. So when we've selected cast iron for all of them, let's change the diameter to what's known. So pipe AB, for example, in the handout, it tells us that one is 400 millimeters. BE, it says on the handout, is 350 millimeters. EF is 250. FA is 300. And then from the reservoir to junction A is 1,000 millimeters. It says, I have a typo there. It says 1,000 meters. That's not right. Let me adjust that. It's 1,000 millimeters for the diameter and the length is 10. All right, we need to enable user-defined lengths, because right now the length that it's assuming is just based on where we clicked for each one of those pipes. So I have to do a user-defined length. So see here, this far right side has user-defined length. I want to click that on for each of them. And then when I do, it'll allow me to edit this length user-defined. So AB is 220 meters. BE is 150. EF is 80. And AF is 180. And then A to the reservoir is 10 meters long. All right, so we've defined all of the properties of those pipes. Let's annotate the pipes. So if you expand on the left-hand side here, the annotations, let's right-click on the word pipe and do a new annotation of the length. So scroll down to length, user-defined. So L equals, and for the offset, let me do a y offset of -2. So that puts it below the pipe where the label is above it. Okay. And let's also add annotations of the diameter. So under the annotations, choose diameter, D equals, and do the offset of the y offset of -5. So we've got the lengths, the diameter. Let's put the flow annotation on as well. So right click on the word pipe, new annotation, and flow absolute. Because if you don't have absolute, some of them it's going to have a negative flow rate just to indicate whether it's clockwise or counterclockwise. All right, so we haven't actually done any calculations yet. We're just setting things up so it looks nice once we do calculations. So I just clicked on Zoom Extents to make it so that it's taking up as much space as possible in the main window there. It's always a good idea to save your work. Let's get in the habit of that. I'm going to save the file here and then make a point. So I'm going to save it in a location that I can easily find later. Don't save it just like on your desktop where you've already got 10,000 other things. You know, create a subfolder to put all this stuff into. So I'm going to call this WaterGEMS in class demo. And then I'll call it Wednesday. When you create that file, it's actually saving more than one file. Let me show you what it saved. So here under WaterGEMS demo Wednesday. Look at, it's actually 6 files. So sometimes students will want me to look at their WaterGEMS and they'll just send me this one. You can't actually open it unless all of them are included. So if you want to be able to have somebody else open and review your WaterGEMS file, you have to give them all of those. So creating an archive is a good way to do that. Here under Save to Package, if you save to package, then you can choose all the things that you're going to include. Just the default is fine. And then save. So now it will, this is the one that if you save to package and then share that with me, I could open it with just a single file. So I wanted to point out the save to package thing. All right, so the last thing we need to do is put the elevation into the reservoir. And so we could go to the flex table for the reservoir, and we know that the reservoir water surface elevation is at 65 meters. All right, let me annotate that. Right click on the word reservoir, new annotation, and it's going to be elevation. I'll do it above, so I'll do it an offset of 3. It's kind of in the same place as the label, so I'm going to turn off the label of the reservoir, and I'll just have the elevation. All right, so when everything's set, and it is, click the green arrow here, Compute. And what it's going to do is it's going to start sucking water through the pipes at the flow rates that you specified at each of those outflow junctions. So F, E, and B, it's going to start drawing water from the reservoir through the network, and then it's going to find out what is the pressure at all of those locations. So we got green, that's good. There's no immediate errors in the simulation. And we know the pressure at B is 434 kilopascals. Anybody get about that same pressure? No? Did anybody? Yes. I got 1 yes. I got 2 yeses. Okay, good. So we know the flow rate that's coming out at each junction, the flow rate through each pipe. So this QAB is 592. And then this Q is the Q that's coming out at B. And then how much is left over is the water that was flowing from B towards E. So 242 is the flow rate through the pipe. We see how much is coming out at E, the pressure at each junction. So let me ask you this. Is the network oversized? What do you think, Matthew? Are these pipes bigger than they need to be?
Yeah.
How low is the pressure allowed to get? What's the minimum pressure that's allowable? Javanti's close, 240. So we can go as low as 240. Are we close right now? No, not even close. Let's just say, just for sake of illustration, what if the pipe sizes are in 50 millimeter increments? So what if I made pipe AB, since that's a pretty big one, 400 millimeters, what if I made pipe AB smaller by a step? So let me open up the junction table here. So I'm going to make pipe AB, where was the lengths? Diameter. Diameter is what I'm changing. All right. Pipe AB, what if I made it 350? Okay, I'm going to push enter. It doesn't change the pressure yet. I'm going to have to compute again. Once I've computed again, now the pressure's 360. So nowhere in the network is it as low as 240. So let me just keep stepping things down a little bit more. So let me take both of these 350s down to 300. Okay, so 300, 300, no, not 0.3, 300, and calculate again. So I'm looking, does the pressure get too low? The pressure is definitely decreasing, and in fact, look at this one, 239. So what's our limit? 240. So I went too far, but not by much, right? So I have to make one of those pipes bigger. Which one is it going to matter? I've been changing AB and BE. If I increase the diameter of pipe BE, is that going to improve my pressure at junction B? No, because that's not feeding the water there. That's where the water's going away from. So I have to increase AB. Let me take AB back up to 350. All right, run the computation. Okay, I'm back into the OK for junction B. I'm back into the acceptable range. There's got to be someplace else where I could save some money. Look at pipe AF. It doesn't need to be 300. Look, 466, 405. Pipe AF is oversized. So I'm going to take AF from 300 down to 250. Okay, let's run the compute. This is optimization. What we're doing right now is iteration. I'm now at 374, 346. I might be able to get away with another reduction in size at AF. What if I took it down to 200? All right, compute. 200, right on the line, 240 kilopascals. That's beautiful. So this is what my pressure would look like under the design condition. So I'm going to save this. This is my network for like optimized pipes. I wonder if I could make any of these a little bit smaller. Probably not, because I'm just right on the threshold. But what does the network pressures look like when there's no flow rate? To do that, I have to go back into the junction table and turn off the demand that was there before. Remember that there's demand at B, E, and F. So let me turn off the demand at B and at E and at F. Turn off the demand, run the analysis again. So compute. Now this is the static pressure. So 582, 544, 616. This is going to be the pressure when nobody's using any water and there's no head loss through the pipes. So what could I do if I wanted the static pressure to be higher? Is I'd increase the water elevation in the reservoir. But it's 11:52. I've stolen 2 minutes from you. And I'll give it back, I promise. I'll pay you back with interest. But hopefully this is useful. You're going to need to have your network sized by Friday of next week. So you should begin playing around with this program immediately. What I'll show you on Friday, actually I'm going to send you a video and Friday. I'm going to show you how you can bring an image into the background and start drawing on top of your network map. So check your email for a video that I'm going to share with you, and then we'll also briefly look at it on Friday.